So hi everyone, welcome to another talk series and apply math and computer science from the MLSES laboratory. Today we have a very special guest, is Martin Verlaan. So basically Martin Verlaan is a professor and senior researcher in oceanography mathematics at Deltars. And for several years, he has been responsible for the coordination of research and development in the field of data simulation and for the scientific coordination and quality control of projects related to storm surge forecasting, marine operational forecasting, Kalman filtering, automatic calibration, design of monitoring networks, operational databases, and tidal prediction. So, Martin, again, thank you very much for accepting our invitation. We are more than glad to have you here. And please, we are waiting for your presentation.
Okay. Well, thank you for inviting me, and I hope we have a nice presentation discussion afterwards. What I'd like to do today is to introduce some of our applications, and starting from these applications, say something about data simulation in the ways we've been doing that, and also in ways forward and different options and problems that appear in there. Yeah, so it will be quite application-oriented, just highlighting some of the problems and solutions in there. So just a brief overview. I'd like to say something into introduction. I'll have a few different applications, first for the North Sea and then at a global scale, and in the end show some of the ongoing, more recent work. Looking at the application. For people living close to the coast in low-lying areas, there's a threat, usually from coastal flooding whenever there's a storm. This is typically a combination of tides that are there every day, although they vary a bit, and storm surges which are related to storms. And these could be extratropical storms at the mid-latitudes or tropical storms at lower latitudes. And of course, this would affect the lives of many people in a very direct way. And one of the ways to help prevent damage and casualties is to warn in advance. And for this, we have operational systems worldwide in many places and try to make the best possible forecasts. Quite similar to the weather, but in this case for the special aspects that are relating to coastal flooding. There's also a control aspect to it, in the sense that in many places around the world, I'm here in the Netherlands, where we have particularly a lot of low-lying land. There are barriers that need to be operated or need to be sort of put in place whenever there's a storm coming up. So this is a particular case in our harbor in the northern part of the Netherlands. And what is particular there is that this is the road to the harbor, and it passes through a coastal defense system, and it needs to be closed during high water. So someone has to go out there and close this door in order for the city not to get flooded. On the right, on the left, you see this barrier at a nice day, and on the right, you see the same barrier with water about 1.5 meters up on the outside of the door. And the lower picture shows the time series. In order to make this possible, we have a forecasting center here in the Netherlands, but there's in many of the surrounding countries and other countries around the world too, where we try to make forecasts of storm surges based on weather forecasts. And well, there's people watching 24 hours a day, and then there's a bigger team whenever there's a storm coming up. The tools that are available, they are, for this talk, for the purpose of this talk, divided in 3 categories. So we have a meteorological model. There's a lot to be said about meteorological modeling and data simulation, which I won't go into today. We'll just use that as our forcing data. So especially the pressure and wind data at the surface that come from the meteorological model is the forcing, the source of the storm surge, and that's being used as input to our models. We'll particularly look in 2 kinds of models. One is a tide surge model, So this is a model that predicts the hydrodynamics, the water flow in the coast, near the coast and in the sea, and a wave model which predicts shorter waves, wind waves that you can actually see at the coast. And those are both driven by the meteorological model. Just to give you a brief idea of what our models look like, it's a bit similar to many other flow type, CFD type models with in this case, a free surface, the free surface of the water. So we divide the water into many cells. We used to do this in a regular grid, but more recently we're moving away from that and using unstructured grids. And many of the unstructured structured grid types, they only use triangles, but we use a combination of mostly quadrilaterals and triangles. And you see a little bit of an example on the right. Within each of the cells, we solve for 3 equations. One conservation of mass equation. This gives a little bit of an idea. So for each cell, we keep the bookkeeping of how much water flows in and out, and that directly relates to to a potential rise or fall of the sea surface. Right, you can look at that in a continuous form or in a discrete form. A lot can be said about this, but this is just the brief slide that I will give, just to give you an idea. The concepts are similar if you're more familiar with ocean models or atmospheric models. We use very, very similar ideas. In addition to the conservation of mass, we have a conservation of momentum, or which is quite similar to Newton's law, but then applied to this body of water in a particular cell. The main forces that we're looking at are tidal potential, so that's actually just the gravity force of the moon and the sun pulling at the ocean water. We have Coriolis force, so the rotation of our planet. We have friction forces related to turbulence, and we have pressure gradients that are caused by the slope of the sea surface. Yeah, and here you see when you put these all together that you can simulate the tides propagating around, and it's important to notice that the characteristic of tides is that they propagate like a surface wave. And because of the rotation of our planet, on the northern hemisphere, it looks like these tidal waves, they stick to the right-hand side. And that's the effect of Coriolis force. You can also see that in some areas, the tides amplify, so you get bigger amplitudes, or they decrease in some other areas. And also that the spatial scales are longer in deep water and shorter in shallow water. This can all be explained. So this is the type of models that we're using. In addition to these models, we also have observation stations, also known as tide gauges, depending on where you are. And this is typically a radar instrument which is down looking and estimates the distance from the radar to the water surface. And I've put a few pictures of what that might look like outside, and you get updated measurements from that. In our country, this is at a 10-minute interval, and these are broadcasted, and we can download and update these and use this. Now, what we'd like to do, of course, is when our models are telling us that the forecast or the model is not going in the right direction at a particular time, we want to be able to use the measurements to update our models. And this is both in real time, which means that during an actual storm, we want to keep the model on track, and also offline in the sense that if we look at a particular historical period and we see systematic differences between the model and the observations, we like to look into this. Well, we use this to improve our physics of the model, the modeling aspects, but we also use this to tune parameters and improve the model in that way. And I've just highlighted here the ingredients that we're typically involved with in data assimilation, which is our models, which we looked at, observations, which we'll also look at. And then as we also need the data assimilation algorithms mix the two. Of course, this also has to be implemented in a computer, and this has to be done in a somewhat logical way. And what we've chosen to do is to work together with a number of parties and implement an open source toolbox called OpenDA, which is freely available. You can just have a look after the talk and see what's going on there. On the right, you see some of the parties that are involved. We're working together to develop and maintain a library that helps us implement data assimilation applications. So it's a library of algorithms. It also contains connections to different models. It's fully open source, and we also use it to work together between the different partners in the projects. And it's maintained by an association to make sure that with an independent group that we like to keep it open and working well, etc. That's what we use as our toolbox here. Let's have a look at calibration first. So when we look at our model for the North Sea, so you see here the North Sea area, and you see an example of a tide gauge there with observed. In the time series, you see observations and model, and you also see the residual. That's the blue curve that gives you shows the differences between the model and the observations. And in the upper graph, you can also see in many locations where we have observations, you can see with the colors, you can see the model values in the back. In this case, this is the amplitude of the main constituent. And you can see the observed values within the circles. And so to give some idea of model performance and comparison to observations. Now we'd like to improve this, and we follow roughly the same this scheme, which is that our model will depend on some parameters that we don't have accurate estimates of in a direct sense, but which are input to our model. We can run the model for a bit, and then when we have observations, in this case mostly tide gauges and later also altimeter data, we can look at the output of the model that corresponds to these observations and compare them. So the better our model is doing, the more closely it will follow the measurements. We can formalize this in the form of a cost function. I've put here a standard notation form where R is the observation error covariance. H represents the mapping of our parameters in this case to the variables that are matching our observation variables. And so you get like a quadratic cost function with weights weighted with the accuracy of the observations. Now you can tune these parameters, change them, and see what happens to the cost function. And ideally, you want to change them in such a way that your cost function becomes lower, so that you have a better fit of the model to the observations. Of course, there's many algorithms available, but I'll go into one particular one that I'll be showing you here. And that's a quite old algorithm, and it's called DUD. And what it does essentially is the following. You first perturb each of the parameters that you have. Then you fit a linear model through these runs. And you use this linearized model that you have then to compute an optimal set of parameters. You run the model again with this new estimate, X star, and see what happens and compute the cost function. Now, two things can happen. Because you approximate, it's either a better solution or a worse solution. Just in case it's better, we'll update the set of solutions that we have and continue from there. If it's not, we're going to do a line search in this particular direction that goes through the initial estimate and the updated estimate and try to find some estimate that is better than the one that we had before. So it's essentially iterative form of least squares that we're applying, which is rather efficient. And we've made many changes to it to make it more robust and I'll go into some of these. If you apply it to the North Sea case, like we did a little while ago, because we have to make one run for each updated parameter, there's a limited number of parameters that we can update. In this case, what we did is there's two, in this tidal model, there's two parameters that we would like to optimize, which is the bathymetry, the depth of the water, and the friction parameter. And we've divided the area up into 100 boxes or areas. And you can see a little bit from the picture on the left, where you see the red lines denoting the different areas. And within one area, the modification of the parameter will be with the same ratio. So it might be that in one particular box, we'll deepen the water by 10%. And then in another box, we might make it 2% shallower. We're talking about small percentages here, so it's just a few percent. The same for friction. And this is then the parameters that we would like to tune using the observations, and the observations in this example are given by the tide gauges in each yellow in each red dot. So there's a little over 100 tide gauges in the area here, and these are all used. If you do this, then you can get a clear improvement of the model, and you can see that the total errors, residuals between the model and the observations goes from 11.7 centimeters on average to 7.8 centimeters. Now this is just an overall average, which you can also see in the scatter diagram below. And we can filter that and sort of try to split that up into what is tides and what is surge, or what is the effect of the gravitational pull of the sun and the moon, and what is affected by effectively from the weather. Because the parameters that we tuned are not related to the weather, we will get more improvement on the tidal part than we get on the surge part. The nice thing about calibrating model parameters is that if you do this properly, then this will improve the quality of your model for a very, very long time. So because the parameters are constant, this leads to a long-term improvement that you will benefit from even weeks, months, or years later. If you look at a particular more stormy case, so this is the result at the tide gauge here in the Netherlands, and we see in black the observations, and we see in blue the model. We see that during calm weather, on the left of the picture, the model is doing very well, and during a storm, it's also doing reasonably okay, but not as good as during calm weather. And this is typical, because during a storm, also other errors, mainly from the meteorological forcing and the boundary conditions, they also play a role in addition to the tidal part of the model. And so in addition to the calibration that we just discussed, we would also like to use our measurements to update the model in a time-varying way to improve our forecast. And then we accept that these improvements will only be valid for a very short time, a few hours to up to a few days, but they will be valuable in the case of a storm. The way we did that was with an ensemble Kalman filter. We used 100 ensemble members, same model as I showed you before. We've assumed that the uncertainty that is important in the ensemble Kalman filter, we use stochastic forcing based on the wind stress, so the surface forcing at the sea surface, and that the open boundary, the boundaries connecting the sea to the ocean, as the control parameters of our Kalman filter. And we also apply a Sure product to remove the effects of spurious correlations. And we also applied some temporal averaging that you can look up in the reference there. We run the full ensemble Kalman filter offline and then derive a steady state Kalman gain for operational computations. The advantage is that because our model, this particular model is near linear, the steady-state Kalman gain works pretty good, and it's much more computationally efficient than a full ensemble Kalman filter, because you only have to run one model instead of 100. Yeah, so that's an important computational aspect in real time. In this case, we only used 32 observations, and the reason for that is that at that time when we were assessing the measurements to be used, these measurements have to be available in real time, because you want to assimilate them at the time when you want to make a forecast now. Right, so there's no time to send an email and ask for observations and wait a few days for it. To give you some idea of the spurious correlations, we've done a simplified example with a coarser model and fewer ensemble members, and then you can see on the left the correlation between Vlissingen at the red dot and the surrounding area. And you can see that in addition to the values, positive correlations or positive changes in the neighborhood of the tide gauge, we also see updates very far away. And then with localization, you're going to remove all the faraway correlations, and you end up with updates that are localized around the particular tide gauge. And of course, you do this for every tide gauge. And this is an important step to limit the number of ensemble members that you need to get a good application. In the end, if you make a run with this whole system, then you can get a clear improvement, which is especially relevant during storms. So you see a bit of calm weather surrounding a storm in the middle of this time period. And in the top, you see the model results compared to observations. Observed is red in this case. But you see that in the lower picture, especially during the storm, the model in black is doing better than above. Right? So it has a clear positive impact. But this is still looking back. In operational forecasting, it's of course important. In fact, almost the only effect is that you want to look forward in time and want to say something about tomorrow, right, or later today. And this is called lead time. So that's the time between now and the time at which you want to predict. So if you want to predict something 24 hours from now, we call that the lead time of 24 hours. And here you see the statistics over a longer time of the accuracy of the model at the Dutch coast, with and without the Kalman filter. And the left bars of each pair, they correspond to the model without data assimilation. Well, you can still see the effects of data assimilation in the weather model. That's the slight increase on the left bars. And you can see that the right bars, the darker ones, that they are much more accurate at short lead times. But in roughly 24 hours, that impact decays. So you only benefit from it around 24 hours. But during a storm, that still gives you good updates that you can use to make better forecasts for later today and tomorrow. Let's see that in action for a particular case. So we have a particular storm, December 5th, 2013. We had a severe storm over the North Sea with strong northwesterly winds. And in the afternoon of the 5th, we had a cold front passing by, which you see on the rain radar. And after that, after the cold front, the winds turned a little bit more to the north. And that's when the water started to increase strongly. When we made a forecast early that afternoon, and now we've cheated a little bit. Of course, now this is a few years back, so I can draw the observations also into the future. So the forecast was made at the point where you see the vertical blue line. And so it's the actual forecast that was made at that time. But of course, the observations were not available. You're in the dark about what happens tomorrow, right? Until you wait after tomorrow. But here you can see that we're under predicting the height of the storm surge for December 6th. And this is by almost half a meter, which is quite significant. And this was quite a significant storm. And then you see when we wait a little bit in time, and make a new forecast. So we have new observations available until the start of the end of the afternoon. And then you can see that the Kalman filter in red is able to update and use this information to create a much better forecast for the next day. So you see the effect of the Kalman filter really in action. Now I want to say something about the waves. So in addition to the mean surface levels or averaged over a time period of 10 minutes, you can also look at waves, which are the short-term perturbations, typically in the magnitude of a few seconds. But they can be quite high, well, perhaps even more so in some places in Colombia than here, but we can get wave heights of a few meters in the North Sea. And we also model these for many reasons, and also because they affect during a storm the erosion at the beach and also the wave attack on coastal defenses. I want to show you this particular example, not so much to explain the full wave forecasting system, etc., but I want to look particularly at a few of the computational effects in a data simulation. This shows the wave equations, which is not so important. What I'd like to say just about that is that we're not actually predicting the movement of the waves, but just the statistics in terms of wave heights at particular frequencies and directions. So that's conceptually what's going on, and you try to conserve the energy and see how this energy or statistics, how they change over time. We can apply a Kalman filter to this, and we found after some study that we think that the main influence is again from the wind forcing, which is of course the source of energy for surface waves. And we used a number of buoy locations which measure wave height in the North Sea, which you can see with the triangles. And we try to apply a Kalman filter to that in order to make some forecasts. Now I want to particularly go into some of the computational aspects. If you look on what you have to do in an ensemble Kalman filter context, is to apply to make a lot of parallel model runs. And so in this case, the wave model is called Swan, so we make a number of parallel model runs. Now, when we reach an analysis time, we have to make an update, and that update requires the data from each of these individual runs. So it is very nice and parallel when you make the forecast, but the updates are not parallel in the same way, in the sense that we need the information from different ensemble members to create the update. Now we looked at a few different things. In this case, the connection to the model was made through the input and output files of the Swan system. This is one of the ways you can connect to and using data simulation to connect to a model. You can try to build it into one program. You could try and make a library out of your model and connect to that. And another way is to use the input and output files of the model, which is sometimes a bit more inefficient, but it's also highly flexible, and it usually reduces the complexity of the implementation a lot. So what we see here is that the model was this setup was quite efficient in terms of running the models in parallel on a cluster and on different computer nodes. And what we applied here was an asynchronous Kalman filter, which means that although we have observations every hour, we only update at intervals of 1, 3, or 6 hours, depending on the different experiments. And we try to see what the performance was like. And what you see here is what the wall clock time for a 7-day simulation is on a different amount of computers. So the number of computers is increasing left to right. I had 4 core machines at my disposal, so this is 4 machines and then increasing number of machines. And you see that by having more machines, we get faster run times, which is not surprising, which sort of stabilizes after a certain time. But when we increase the time interval, so we lower the frequency at which we update the system state, we get a better performance, and that is because the number of points at which we have interaction with the model decreases. But of course, this model is nonlinear, so it also decreases the performance somewhat. So we get, in this case, a little bit of a trade-off between the accuracy, the nonlinearities of the model, and the computational performance. But you can see that the asynchronous filtering works quite well in a case where you have where the access time of the exchange of information between the model and the data simulation algorithm actually does play a role. And so that's a computational aspect that is quite significant. And you can look at that, you can do that at different resolutions. And because in this case, a wave model has a particularly large state because at each grid cell, it has variables for each direction, and there are 36 directions, and there are 32 frequencies, so that there's a few hundred variables at every grid cell. That's why it has a significant state even for relatively modest models. And well, here you see that for larger models, computer times, of course, increase. But the asynchronous filtering really works well in increasing the performance. To continue this line of larger and larger models, more and more data, I'd like to say something about a more recent application. In addition to some of our regional models, we also built a global scale tide storm surge model, which has roughly 2 million cells. And we're moving towards even higher resolutions. If you compare that to when I started my career, I started with a model that had approximately 5,000 cells. So that's the order of magnitude it has grown over time. And this is still increasing quite rapidly. At the same time, when I started, I had, for the Kalman filter, we had 8 locations that were available in real time. And if you look globally now, there are over 500 locations, tide gauges that are available. And this is not even looking at the other options that we have. This is just the tide gauges. Because there's also satellites that measure the water level. In this case, an example, I think it's Topex. But there's several satellites that measure the water level continuously. So that's an additional source of information. Now let's first look at the calibration case for this model. The basic setup is the same as in the regional model. So the parameters that we'd like to tune are still bathymetry. And now we have 2 types of friction, but that's not crucial for now. You can see that the friction, the bed friction, lower left, is localized in shallow areas with large tides. And there's another type of friction which is not so localized, is also a bit localized, but not necessarily close to the coast. We did a sensitivity experiment, and we found that the sensitivity for the bathymetry, the depth of the ocean, is much larger than for the other 2 friction parameters. So we'd like to look at bathymetry first. In order to come up with a good parameterization and optimization scheme, what we first did was we looked at the problem in a bit of an analytical way, using some of the partial analytical solutions that there are to come up with an estimate of the length scale. I've shown you that on the top right, and there you see that assuming an accuracy of a few centimeters from the satellite, this gives an idea of the length scale of waves that we can resolve. And so this is the scale of estimation that is possible with the data that we have. It's a rough estimate, but it gives us something to go by. So you see, for example, in the Arctic, because of the relatively low amplitudes, this is more difficult than in, for example, in a coastal sea. To continue this, we divided the ocean in many segments, and we did a sensitivity experiment, and you can see in color in the lower right what the sensitivities are for each of these boxes. And you can see that in some places the solution is quite sensitive to changes in the bathymetry, and in others it's not. And the sign of the sensitivity also changes from place to place. We're using the same algorithm in this case. There's a few things that we changed to this in order to make this problem manageable. And one thing that we did was add hard constraints. So in addition to the least squares problem, we're also providing hard constraints in the form of maximum, limiting the changes to be a maximum of 10% plus or minus. And that's implemented. So if the algorithm reaches this hard constraint, it's more or less like a quadratic programming solution. It will not exceed this value. Of course, what we also need is that the model runs themselves are all running in parallel, so we can do all this stuff on a cluster, of course. We're running with a calibration period of 2 weeks, and then we ran into a new constraint that we didn't have before, is that 2 weeks is about the limit with these number of observations and these number of parameters to keep the whole least squares problem in memory. So if we were still solving the least squares problem on one node, and this is about the limit that we can get. Even though we're doing the runs on a cluster, that is the limiting part at this moment. We're now working on an improvement on that, but this was at that time the limit. To lower the computation time, we tried two approaches. One is to, in the calibration, replace the model with a lower resolution model that makes it much faster to run. And then what we do is we take the bathymetry corrections and apply them to the fine resolution model directly. And we did a slightly different modification, which is a bit inspired by incremental 4D-VAR, where instead of doing the calibration directly with the coarse model, we make a model run with the fine model, and then compare these to the observations, and then look at increments only. So we have changes in the coarse model, HC, and we approximate the solution, correcting for the bias between the fine and the coarse model. And we expect this to be more accurate because we're removing a lot of the bias from the calibration process. So here you see the cost function of the calibration over time. You cannot directly compare the two cost functions because they don't have the same cost function, but you can see the evolution over time. So you see first the initial runs. We have 110 parameters, so we do 111 runs, so the original run plus 110 perturbations, and then we start the least square solutions, and then you see that the method is quite effective in optimizing the parameter settings. This is in terms of cost function. This is in terms of parameter changes. So you can see how the parameters change over time. You see that in the initial 110 runs, we modify one parameter at a time. That's why you see this pattern. And then the optimization process starts. The processes for the two different approaches, they were actually quite similar in this case, which you can also see from the parameter changes. Although there are differences, there are also quite a lot of similarities between the two solutions. And although we expect approach 2, where we use the increments to be more accurate, in practice it turned out to be not a lot more accurate. And what we think it was is that because of our limitation to the calibration period of 2 weeks, so we couldn't fit more observations in, and 2 weeks of observations was actually too short. But in order to extend it, we have to modify the algorithm, which we're doing at the moment, and that was probably the main shortcoming, so that the model was overfitting the data. There was a lack of good data to fit to. Or actually, the data was not missing, but the capacity to handle it. Here you see what that amounts to. There's a lot of numbers, but what I wanted to show you is that even though the model is reasonably accurate before we started calibration, that in the various approaches, so on different time intervals, but also in fine and in coarse resolution and with both approaches. There's a clear improvement of the model, and you can look at this in many different ways. You can also look at the accuracy of the model in space. So here you see in color the accuracy of the model after estimation. That's the yellow reddish colors, and the difference between before and after calibration, which should be bluish because that denotes an improvement of the model, a lowering of the RMSE errors. And you can see that in most areas there are improvement. There's only a few areas that stay the same or become slightly worse. This is the same period. This was the same period as we used for the calibration, but of course we also look at other validation periods to see if the improvement of the parameters actually also works for different time intervals. So that's actually really an improvement of the parameters, not just a fitting of the coefficients to the particular data set. That has no physical meaning. We also took a very different data set, which is tide gauges around the world, but also here you see a clear improvement. Yeah, just to give you a flavor, there was where you picked one particular tide gauge station, the two different approaches, and then really at the bottom you see the residuals because they're all pretty close to the observations, and you can see that before calibration the blue line has a larger amplitude than after calibration, and there's a quite clear improvement from the calibration itself. So that's the overview of the different applications that I wanted to show you, and then give you a flavor of some of the applications that we're doing with data assimilation, both in calibration and in ensemble Kalman filtering. So thank you. If there's any questions, then fire away.
Okay. Thank you very much, Martin, for these very, very nice presentations. I think all the cases you present are practical and are more than of interest for all of us. We are, entering in the world of practical data simulation to solve real life problems. So yeah, we have some questions from the audience. So the first one is Janice Juliet. She asks, did you base on previous investigation for the RMSE value for data model?
I'm not sure I 100% understand.
So maybe, yeah, I think the question is whether you employ historical data for the estimation of, just to check that actually you are improving the RMSE, something like that.
Yeah, so we tried, so there were two applications on calibration, of course, and yes, and that's important, I cannot emphasize that enough, that if you calibrate or assimilate, it's always important to have another data set that you separate out to test whether you're actually improving your forecasts or your estimations. That's really important. So yes, that's what we always do.
Okay, excellent. So yeah, we have another question from the audience. So are those constraints region based or just to maintain physical sense of the problem? So I am with regard to the constraints, the local boxes.
Yeah. So there's two types of what you could call constraints. We had hard constraints in the final example, which are in our case meant for the following: if you're convinced that the parameter that you're tuning is actually the main source of error, then in principle having weak constraints, which we also have, should be enough to regularize the problem and to get good estimates. But in a large-scale application, it's very difficult to not have some kind of interference with the physical effect that you're not accurately representing, etc. So we have this as a catch to make sure that whenever there's something wrong, we're still getting reasonable estimates. And the other aspect in constraints is the regions that we're showing, we constrain the parameter, the way we tune the parameter is constant in a relative sense over this region. So we adapt the bathymetry, for example, by 1% for the whole single box. And the reason we do that is there's a limited amount of information in the observations that you have. So you have to regularize the problem in some way. And one way to do that is this. You could also have an a priori covariance estimate that you provide as an additional constraint, or you can provide other kinds of additional constraints, but you need to regularize the problem in such a way that the solution becomes unique, or at least much more constrained than it is without this. We cannot just start estimating individual the bathymetry in individual cells without any constraint. That will not lead to a reasonable solution.
Okay, so basically you enforce that the physics and the dynamics on a neighborhood for local boxes, right? So local boxes share their boundary, and then you can constrain that the physics from one box to the other are continuous, right? Like a continuous. Yeah. Makes sense. So I have a question. So before we move to another one from the audience, with regard to the you mentioned, and for me is a very interesting part because it's actually my field of research, the regularization part, right? So in order to calibrate the parameter of the model, to tune the parameter of the model, you compare the information coming from the model, the observed components, with observations from a neighborhood. Based on what I saw in your slides, you have an evenly distributed network of observations. So you have enough information. So my question is with regard to, since you are not a priori employing a prior estimate of the background error for the entire domain, for instance, how do you what criteria of regularization do you employ to reduce the impact of the observations, the noise in the observations? So how do you regularize this J of X cost function, which compare information coming from your model and the information coming from the observations?
Yeah, and you're talking about the calibration case here now?
Yes.
Okay. Yeah. So we regularize the solution in a number of ways. So the first one is, like I discussed, we reduce the number of parameters by restricting the modifications to be constrained, to be similar or the same within a certain region. And that we made sure that there's a smooth transition, but that reduces the number of parameters a lot. So we have in the last example, we have about 2 million cells. We divide them in roughly 100 regions, and in each of these regions, we modify only by a fixed percentage. That is a strong constraint. The second one is we limit the constraints with a background term in the cost function, which is diagonal in our case, and is also about 10%. So there's a weak push back towards the original estimate. And then the final one is that in case something goes wrong, we also have a hard constraint to make sure that it doesn't give very large modifications, which have nothing to do with the bathymetry correction, but probably some other physics that is missing in the model.
Okay. So we have another question from the audience. When you said that you were calibrating the model using a low resolution model, that model was a little version of the high res model, or two different models?
No, so it shares everything except the grid with the other model. It's just a lower resolution version. Yeah, and it's important that your low resolution model still reasonably represents the observations that you want to assimilate, right? So in our case, we threw away some of the observations because they were in areas that we didn't think the low resolution model would be capable of reproducing. We restricted the solution to deep water in this case, and then we get reasonable results with a much faster solution. Yeah, so one of these runs in the end, so one calibration run takes about 20,000 core hours for this 2-week calibration to give you some idea. So it's a week on the cluster.
Okay. So, Martin, I have another question with regard to the localization. So we know that we employ localization to avoid the impact of spurious correlation.
Mm-hmm.
Well, by what I know from your presentation, you may using Gaussian model, right?
Yeah, that's true. Yeah.
So, an open question that is on the literature and in many parties, how do you calibrate the areas of influence when you perform the localization on the background error covariance matrix?
Yeah, that's tough and laborious. Yeah, that's really one of the drawbacks, I think, of this Sure product. In principle, when properly tuned, it's very effective. But when you start an application, then you have, in addition to all the other degrees of freedom that you already have, you have 2 additional degrees of freedom, which is the number of ensemble members and the localization radius. And the bad thing is that the experiments from a lot of literature show that these 2 are connected. So when you change the number of ensemble members, the optimal localization radius also changes. So this is essentially a trial and error method, although there's some research in trying to improve this and correct for it. But in the basic way that many people are using it, this is a trial and error approach that is really laborious, because so you make a guess of the ensemble size and then you start fiddling with the parameter in quite expensive experiments often. The good thing is once you've got it all fixed, then you can keep it for a while, right?
Yeah, that's a good point, actually. Yeah, and the issue also that we know that this localization radius, can induce imbalances in the posterior ensemble members, right? We can get something like that. Then we have another question from the audience, actually. How can we collaborate with OpenDA project? This is from Luis Gabriel Guzman Reyes.
Okay. Well, thanks for your interest in many different ways. There's you can if you're using one of the models that is already connected to OpenDA, you could just have a look and see if it helps you in solving the problem. A lot of the models are open source as well, so you can have a look and see if that fits your problem. It's also possible, if you're using a different model, to connect your own model to OpenDA. And there's quite some examples, and there's course material, etc. If COVID goes away soon, we're also doing summer schools and courses regularly to help you train. And if you become experienced, you can also develop your own algorithms and contribute to the source code. And you can contribute in many ways. It's really open source in all respects.
So I have another question from Felipe Acevedo. Is convergence guarantee using those low and high res models, keeping interpolation in mind? Thanks.
Yeah. Well, thanks for that question. So no, there's no a priori guarantee that this approach will work. What you're trying to do is what you hope for is that the starting point is that your high resolution model is too expensive to employ directly, and then you try to reduce the computational time in various ways, and one is in reducing the resolution. But the lower resolution model still has to mimic the same kind of behavior as a high resolution model. It can be a little bit less accurate, but it still has to mimic the same behavior. And that's really crucial in getting a reasonable performance, because otherwise you get an update of your parameter of your state variable, and then when you put it back into your high resolution model, it doesn't actually improve but deteriorate the result, and then you're stuck. And so there's no a priori guarantee. You rely on a good connection between the two.
Okay. We have another question from Oscar Alvarez about applications for coastal management. How does your result reach the community and other authorities?
Well, there's many different answers to that. So first of all, the modeling system that we're using is open source, so any community can download and start developing their own environment. We also publish our results to help and inspire this kind of work. At Deltares, there's also a lot of work going on where they develop systems, especially for governments in different countries. And finally, we have in terms of the coastal forecasting, we have a global forecasting system, and the forecasts of that, they are available openly on what is called blueearthdata.org, and so anybody can have a look at our latest storm surge forecast worldwide.
Okay. So for another one, have the result of research been useful to convince your authorities to improve your coastal monitoring systems?
That's a nice topic as well. So typically, monitoring systems have been designed by different various constraints over time until a certain point. So in the case of tide gauges, many tide gauges are near harbor, so to help support the harbor authorities. And if you're looking at the tide gauges or measurements in general in terms of helping make a better forecast, so in connection to the data assimilation systems, you sometimes want to put the measurement systems in different places. Well, first of all, we have to, from a mathematical side, we have to be a little bit modest about this, because there's a very much practical constraints, because you have to get power to the measurement system, there has to be communication, it cannot be in a shipping route, etc., right? So but we have been in contact with authorities in several countries in helping them optimize their monitoring systems. In terms of data assimilation, this is actually an interesting topic. There are many papers on what are called OSSIs, observing system experiments or observing system simulated experiments, where you can see how you can use data assimilation system to make an optimal design of your network. It's an interesting field.
So we have another from the Mathematical Modeling Research Group. How can we properly quantify the impact of observations on the filtering problem? Verlaan 2016, can this be pointed into a real problem?
Yeah, so when we look at the impact of observations, yeah, that's quite a topic in itself. And the simple answer is probably you can make an experiment with and without a particular set of observations and see what the impact is. And depending on your application, if it's for forecasting, you also have to look at forecasting accuracy. So you can do these experiments for historical time periods and really get hard numbers on this. The difficulty is that the number of possible configurations and modifications grows so rapidly that you can never try everything you would like to try. And so there's also a lot of development on methods to help support this type of decision. And yeah, we've been also working a little bit on that, where you try to use the equations of the optimization to see whether you can, which observations are contributing in what amount to the accuracy of the forecast.
Okay, excellent, Dr. Martin. So I have just a last question. What do you recommend to countries wherein observations are not dense? So for instance, in Colombia, we have like regions in which we have a bunch of observations, but we have another ones with sparse observational grids. So what do you recommend in those cases to perform data assimilation?
Yeah, so traditional measurement networks are quite expensive. And so if we look at the networks, the existing networks, then the typical traditional measurement, so the combination of the equipment, the maintenance, the telecommunications, the power, etc., adds up to quite a sum. If you want to, what we've been seeing, I think there's two developments that are, or perhaps three, that are interesting. One is satellite observations. There's more and more satellite observations that are freely available. They require a lot of expertise to make proper use of, but I think that's an excellent source of information that can contribute a lot to many applications. The second is that our networks of volunteers, so some parameters can be measured with quite simple means by volunteers. So, for example, there's a test ongoing in a region not far from my house, where they have a QR code on simple gauges, and volunteers, they can read the water level, scan the QR code, and send that up to the server. So that makes it relatively cheap and robust way to add measurements to your system, to use the public in helping making observations. And the third thing is the changes in electronics and telecommunications. There are now more and more low-cost observation systems, where you don't have the telecommunications in a traditional way, but with more cell phone type technology, with cheap sensors, etc. And there's a lot of development in that sector too.
Okay. Okay, excellent. So, Dr. Martin, thank you very much again for accepting our invitation. Thanks to all the audience for listening this very, very nice presentation on data simulation and how can be to put into practice for solving real-life problems. So, I don't know. Thanks to everyone again, and bye-bye. Take care of you.
Yeah. Thanks. Bye-bye.